First, let's look at the insertion of the minimal heap. Here, we have a binary tree, right? So first, we have to determine if this tree is a minimal heap or not. So the property of a minimal tree is, firstly, that it is a complete binary tree, and that the value of each node must be less than or equal to the values of its children. So let's begin by determining whether our example is a complete binary tree or not. A complete binary tree is defined as a binary tree that has all its nodes filled in from the top to bottom and left to right, where there aren't enough elements, so the nodes below the right side can be left empty. Let's look at our example binary tree. The tree's nodes are filled in starting from the top, going down, and from left to right for each layer, because we are running out of the nodes to fill the tree, right? So we have to leave this area on the bottom right empty. So our example is indeed a complete binary tree. Next, we will determine whether the value of each node is less than or equal to its children. First, let's look at the first node with value 6. The node children have the value 9 and 10 respectively, so 6 is indeed smaller than 9 and 10. So the parent node 6 satisfies the condition. Then we will look at the node with value 9. The node 9 is smaller than the value of its left and right children, which is 15 and 12. So node 9 also meets our criterion for node 10, since it has no left or right child nodes, and we don't need to do a comparison for 15 and 12. And after we're looking for these properties, we can conclude that this binary tree is a minimal heap. Now, we want to insert a node with value 5 into minimal heap. First of all, when we insert a node, we insert it into the bottom right to maintain a complete binary tree. So the position of the 5 must be left child of the 10. If the 5 is the right child of the 10, then this binary tree is not a complete binary tree, right? Because we didn't put the node into from the left to right. So at this point, we put the 5 as the left child of the node 10, and after we construct this binary tree into a complete binary tree, we also need to satisfy the second property of the minimal heap. That is, the value of each node is less than or equal to the value of its children. But at this point in time, this node is bigger than its child node 5. So what should we do in this case? We should exchange 5 and 10 for each other. And after 5 and 10 are exchanged, 5 is less than 10, which will satisfy the property of a minimal heap. But the node 6 is still bigger than the node 5. So what we're going to do at this point is exchange 5 and 6. And after exchanging, at this point you can see our current binary tree is still a complete binary tree, and the value of each node is less than or equal to its children. After all that, we just put 5 into its correct position in our previous minimal heap. We define add function, which is used to insert an element into a minimal heap. And when the element is added to the minimal heap, the real set attribute is incremented by 1 to reflect the new number of elements in the heap. And then we check if the number of the element in the heap has exceeded the maximum allowed heap size. If the condition is met, we just print the message added too much element and decrement the real size by 1, and then returns without adding new element to the heap. This check helps us to ensure that the heap does not grow beyond its allocated size, which can prevent any potential issue with memory allocation or data management. And when we're working with limited resources, or when a specific heap size is required by the problem domain, this constraint is particularly very useful. And then we add the given element to the heap by placing it at the end of the underlying array self-heap. The self-real size variable keeps track of the current number of the elements in the heap, since the array indices in Python start at 0. So by using the self.heap as self.realSize, we are adding the new element at the next available position in the array. And then we assign the index of the newly added element into the underlying array self-heap into the variable index in the previous step. Since the element was added to the end of the array, its index is equal to the current number of the element in the heap, which is represented by the self.realSize. So in this heap's underlying array self-heap, we try to calculate the index of the parent node of the newly added element. The heap is represented as a complete binary tree, which is by using an array with the root node which is stored at index 1, which leaving the index 0 is unused. So the parent node index is node index floor divided by 2, and the left child node index is the node index multiplied by 2, and the right child node index is the node index multiplied by 2 plus 1. And then after we added a new element to the heap, we have to restore the heap property. We just repeatedly comparing the value of the newly added element with its parent node, and then we swapping their position if it is necessary. The while loop runs as long as these conditions are met. The first condition is if the value of the newly added element, which is at the index, is smaller than its parent node, which is at the index parent. And the second condition is if the index of the newly added element is greater than 1, so that we can ensure that it doesn't go beyond the root of the heap. So inside this while loop, we perform the following operations. First, we swap the value of the newly added element and its parent node since their positions have been swapped, and then we update the index of the newly added element to the index of its parent, and then we recalculate the index of its parent node by using the update index value, which is assign the index floor divided by 2 to its parent. And this loop will continue until the heap property is restored and the newly added element reaches its correct position in this heap.